Okay. Couple things I want to mention. One is I'm starting to put all this review stuff, all the material you need to study for the final exam. Um, so I have made, okay, I should back up for a second. One thing I should mention is I'm not here tomorrow, but my graduate student Dylan Frang will give the lecture. He will play the video for the review of material past quiz 6. So I just recorded a video for that. It's already up. Yeah.
You have office hours
Yeah. So, well, okay, I won't have office hours when I'm away. I have office hours today, but tomorrow I won't because. Okay, so I'm driving to Canada yet again. To this time to New York University. If somehow I'd gotten it together, I could have just gone to both 2 days, one after the other, but I'm going again tomorrow. Yes. But I'll be back by midday Wednesday. So what will happen tomorrow is, okay, let me tell you the little schedule. So today we're going to finish all the material for the whole course. You'll know everything you need to know by the end of today. Okay. And then tomorrow, Dylan will show the video for a review of quiz 7, or the after quiz 6. There'll be a little time left, and so you'll probably show one of the new videos that I've just recorded as well. I haven't decided exactly which one. Actually, maybe I'll ask you. So the review of quiz, quiz 6 is only 15 minutes long, so we can put in another video. Would you like to see the review of quiz 1 material, review of quiz 2 material? Would you like to see something else? Any preferences? You want me to surprise you? Okay, I'll just make it for you. Right? Because these are things you haven't seen before. I wrote those reviews after the quiz 1. So maybe not quiz 1, because quiz 1's kind of easy, right? So let's have Dylan do quiz 2. That's with the projectile problems. Remember, those are kind of all right, and then on Wednesday, we'll just do problems. I'll take all requests. So there will be what's on the Diesel website now. You'll see here I added some extra practice problems. If you go to the folder of practice problems, there's something called Waves A with solutions. There's something called Waves B with solutions. And then I've updated the list of practice problems listed according to quiz. So I have the list of quiz 1, quiz 2, quiz 3, quiz 4, quiz 5, quiz 6, quiz sort of 7, which is beyond quiz 6. Okay.
Is it possible that you can have a practice exam, like same kind of formula that you're going to have?
You mean a practice exam?
Yeah.
Yeah, that's the next thing I was going to say. We are finalizing 2 practice exams. Okay, that will be posted probably by the end of today. Right? We're having a meeting, a course meeting this afternoon. So that will be up. I'm going to record the solutions to those 2 practice exams later this week. I will record. I've got a lot of recording to do because I also wanted to record videos covering quiz 1, 2, 3, 4, 5, 6, which I have not done, as well as practice quiz 1, 2. I think I haven't done either, so I would have to think to record that. But in the end, you're going to have like 24 hours of material to review if you want. Okay, so there will be a ton of stuff, hundreds of problems. Okay, any questions? Good. Okay, so let's get to finishing what we said about standing waves on a string. So we already started this last time. Let me just make sure we're recording. Yeah, okay. Where's this coming? Standing waves on a string. Okay, so we produce these standing waves that go up and down rather than traveling. So they look kind of like this, they oscillate like this. And I have a demo that will show you that. Okay, to be honest with you, the demo cheats a little bit in that it actually goes around in a circle to make it easy. gives you the idea. Here's the fundamental mode. So this is having an antinode in the middle. There's nodes at the two ends. Okay. And then what I can do is here's one with something that goes back. Here's one with six with node in the middle here. These are what we're calling antinodes. Okay. So see that? Alright, and I can hear the three. So, like I said, these are the nodes, and these are the antinodes. Here's another antinode. Okay, now let's consider a string with a fixed length L. Okay, so let's say the length of L is like this. And we're going to consider various possible ways the string can vibrate. So we need to have nodes on the ends of the string because the ends of the strings don't move. Okay, how do I get rid of this? I have no idea. Okay, it just goes down. All right. So let's do what's called the n equals 1, or what's called the fundamental mode. So when you play a stringed instrument, you are exciting this fundamental mode, and what happens is the string just vibrates like this. Okay, from one node to the other at the ends. And you'll notice that this is half a wavelength. So half a wavelength, because it only goes up and comes back. It doesn't dip down and then come back. So the half wavelength is equal to L. So you can deduce that if half a wavelength is equal to L, then the full wavelength, which we write as lambda. So let me call lambda 1 for the first. It's called the first harmonic. I'll write that later. This is also called the first harmonic. First being n equals 1. And the wavelength lambda 1 is equal to 2L because half a wavelength is equal to L. Any questions about this? Okay, let's go on. So let's go to n equals to 2. And I will use a very non-scientific terminology for this shape. I will call this a football, okay, because it looks like American football. Right? And so instead of having just one football, I can have two footballs spanning the length of the string. Okay. So that's n equals to 2. And this is what's called the second harmonic. And now in this case, we really do have one wavelength, one full wavelength for the full L length here, between here and here. You can see that. So therefore, in this case, lambda 2 for the second harmonic, is equal to L. Okay. Now in general, I'll just tell you the formula. In general, the nth harmonic, where we have n footballs. Okay, the nth harmonic has lambda n is equal to 2L over n. If you're wondering how I got that, it's pretty straightforward. I'm calling these little things footballs, but a football is half wavelength. Okay? So if I have n footballs nose to tip, touching each other, then I have n times half n times lambda over 2, half wavelength, is equal to L. You can solve for a lambda, and then you end up with 2L over n. Does that make sense? Okay. All right, it's not a hard derivation. But we get that for the nth harmonic, the wavelength is 2L over n. Now let's talk about what the frequency will be. In order to get the frequency, I need the wave speed. So if the wave speed is v, then we know, since v is equal to lambda times the frequency, this is just a general formula for waves. The wave speed is the wavelength times the frequency. Remember, wavelength is meters, frequency is inverse seconds, so it gives a speed, meters per second. And so that means we can solve for the frequency as v divided by lambda. Okay? So I just told you there was a formula for the wavelength for the nth harmonic. So the frequency of the nth harmonic, and let's use the label f sub n, makes some sense, is equal to v, this wave speed, divided by the wavelength, lambda n. Okay. And so we get v divided by, okay, let's just do the derivation since it's not hard. We said lambda n is 2L over n, and so I get the denominator of the denominator is the same as the numerator, so I get nv over 2L. So the formula is Fn is equal to nv over 2L. Thank you. All right. So that's the formula for the frequency of the nth harmonic. Okay. So if you want me to put the two formulas together, we also have this formula that the wavelength was 2L divided by n. So you want to put these two together for the string. Okay. Any questions about this? Okay, now what we're going to do, so I asked last time how many people have played a string instrument. How many of you have played either a woodwind or a brass instrument or a pipe organ or one of those instruments? Quite a few on that. Okay. So these are related to sound waves in the pipe. So let's talk about that. Standing waves. Pipe. Okay, it's basically an air column. Now, this is a little bit more complicated, and with the string it's easy to visualize what's going on. The string either goes up or it goes down. With air, what's happening is, let's say the air column is like this. The air can be vibrating back and forth like this. Okay? And there can be places where there's a node, meaning the air doesn't really move at all. Or there's a place where it does vibrate back and forth. All right? So what we're going to do, when I make a plot of, I'm going to draw the wave like a transverse wave, even though we know it's not a transverse wave for sound. It goes like this. But it's hard to draw these longitudinal waves. So I'm going to cheat a little bit. And what I'll do is I'll make a drawing of the displacement. So let's say going up means forward displacement. and going down is backwards displacement. And then I can draw what's happening with, as a function of x, what's going on with these waves. I can have something like this sort of behavior. All right? So, and it changes with time. I get a nice standing wave like this. This is 0, and then pass through. Okay, so then we can talk about, here's a node, here's an antinode. Just like we did for a string, except we're talking about forward and backwards displacement of the arrow. And now, for the string, the rule was when we pinch the two ends, we had to have a node at the ends of the string. That's why the footballs always had their noses at the ends. For the case of the pipe, it depends actually on the kind of pipe. Okay, so we can have there's two types of pipes that we're going to discuss. And so the ends can be either open or closed, meaning, either it's exactly what it sounds like. Either it's open or it's closed. It's sealed or it's open. Okay, so let's talk about, this is what I'll call an open pipe. This is just my shorthand, meaning open on both ends. Okay, or we can have an open, closed pipe. And this is open on one end and closed on the other. Typically we draw the pipe, and we draw which side is the closed end and which side is the open end. So closed open really doesn't make a difference. You just flip it around. Okay. But you might ask, what about the closed pipe where it's closed on both ends? Well, that pipe doesn't make much of a sound. So we don't even consider it. If you close it on both ends, you're not going to hear what's going on inside. So we only consider the open or open closed pipe. And the main thing, let's consider this, what I call the open closed pipe. Here's an open closed pipe. Okay, so this is the closed end, and this is clearly the open end. All right, and the thing about the closed end, let me try to draw this correctly. The thing about the closed end is that we need a node. We need a node at the closed end. Why do we need a node at the closed end? Because we have a barrier there, and the air can't smack against the barrier. It just doesn't like to do that, so it stops moving, right, the barrier. Okay. And so we need a node there. Now, at the open end, it's sort of the opposite. What we need in that case is we need the pressure across across this opening needs to be even. So as a result, it turns out we need an antinode at the open end. Okay, so it looks kind of like this, where we have to have a node here, just like for a string, but then we need an antinode at the closed. At the open end. Questions about that? Okay, now we can then classify what's going on with the various pipes. So let's first do the open pipe. And the rules for the open pipe, so remember this is open at both ends. So we need to have an antinode at each of the two open ends. So let's draw like this. Here's my pipe, and it has a length L. So the longest wavelength possible would be to have just something like this, where we have an antinode on each end and just one node in the middle. Okay? And this is what's called n equals to 1. This is the fundamental mode, or first harmonic. Okay, now if we're trying to keep track of this, this is a lot like what we had before with our string, but in that case, when we have the first harmonic, it looks something like this. Okay, but if we're trying to keep track of these open pipes and stuff like this, notice that this is half a football. Okay, remember I'm calling these things footballs. If you came in late and you're wondering why the heck this guy's talking about footballs, if this is what I mean, this thing looks like a football. So you cut this football in half, and notice that I have half a football here, half a football there. So in terms of the actual length of this thing, this is a full football. Everybody see that? Okay. So the wavelength ends up being the same as for a string. So you end up getting that lambda 1 is equal to 2L. Okay. And then if we want the frequency, it's just V over lambda 1. So then it'll be V over 2L. Just like the string. Questions about that? Everybody okay with that? Yeah. 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 There's some places where it goes below atmospheric pressure and places where it goes above. It oscillates. It's similar to what? Yeah, it's a bit like tension. If you want to get that, it's pressure waves. Okay. And we can have the n equals to 2 mode. Now what we need is to have 2 nodes in the middle, like this. And again, this is very similar to what we had for the string, in that we have, here's one football, and there are 2 halves of football, so I get 2 footballs. This is n equals to 2, and then I get the same formula, n lambda 2 is equal to L. Okay, that's 1 full wavelength, and F2 is equal to V divided by lambda 2, which is equal to then just V over L. Okay, in general, the nth harmonic, okay, I forgot to say this is called the second harmonic for n equals to 2. N equals to 2 is the second harmonic. In general, the nth harmonic has the same formula as for the string. Lambda n is equal to 2L divided by n. You don't have to learn a new formula. And Fn is equal to the speed divided by lambda n. Plug in the formula, and you get nv over 2L. Okay. Questions about that? Everybody follows that? Not so hard stuff, right? Okay. Good. Go on then. All right, so we did the open pipe. Let's do the open closed pipe, and that's a little bit different because of the fact that the ends are different. So let's do the open closed pipe. All right, so that's open on one end, closed on the other. Okay, so we have the pipe is the length L again. let's draw the longest possible wavelength we can get. So we need a node at the closed end, and we need an antinode at the open end, so it looks something like this. So this is half a football. Okay, I cut one of these footballs in half. So half a football is a quarter of a wavelength. So this is, we call this again n equals to 1, the fundamental mode. So fundamental mode, or first harmonic. And I said it's half a football, so that's a quarter of a wavelength, so the whole wavelength would be 4L. So it's a little different. Lambda 1 is equal to 4L this time. And then the frequency will be V over lambda 1, so it'll be V over 4L. So a bit different. Okay. It'll be lower frequency. Now if I go to the next one, now the counting will be a bit different here. We're not going to do n equals to 2. We're going to call this one n equals to 3, and I'll try to explain why we call it that. Okay, for the open-closed pipe, we don't actually count footballs, but what we do is we count half footballs. So I have a half football here, that's 1 half football, that's n equals to 1. For this open-closed, for the next one, I count, here's half a football, here's half a football, here's half a football, so I call this n equals to 3. So I skip n equals to 2. So I go to n equals to 3. No n equals to 2. Okay? Only odd ones. Only odd n. And so we call this the third harmonic. And so since we have 3 half footballs, that's 3, right? That's 3/4 of a wavelength fits in L, and so this ends up being 4 over 3 L. And then if I, oops, sorry, I wrote the wrong one. I was ahead of myself. This is the wavelength. It's wavelength. Lambda 3 is equal to 4 over 3 L. And then the frequency will be V divided by lambda 3, and then I get 3V over 4L. Okay. Oops, sorry. Any questions about that? So we have only odd harmonics. And the general formula is for odd n. In other words, n equals 1, 3, 5, 7, and so on. We get the formula that lambda n is equal to 4L over n. That's the formula for the wavelength. And the formula for the frequency is equal to NV over 4L. So instead of 2 L's, in this case, you get 4 L's, but you have to do odd integers. Okay. Any questions about that so far? Everybody got that? Okay. Next topic. Okay. Now, remember we talked about, in my notes I repeated, but I did this recently. So, we talked about constructive interference when things go up and down together, right? They add together and they increase the signal. And if they go opposite to each other, then they cancel out and give zero. Okay, so constructive is when they add up together. Destructive is when they cancel out. So we're going to talk about when we have. So any of you have ever tried noise canceling headphones? Have you tried that? Okay. So that's an example of destructive interference. What happens is you have a receiver that your headphones that picks up the signal, the sound signal, and it actually generates another signal that's 180 degrees out of phase, or pi radians out of phase, and puts it back in to your ears, together with the original signal. It has fast electronics, so it can do that very nicely. And as a result, it cancels out the signal. Kind of cool. So we're going to talk about this kind of effect. So let's suppose we have 2 point sources of sound. Okay, let's say 2 point sources of sound. Let's say S1, and we might, so, oops, I wanted to make these look concentric circles, so let me try to do that a little bit better. Okay, so these are wavefronts. They're showing points with the same phase, just off by 2 pi's. Okay, 2 pi radians difference in phase. And then maybe I have another point source over here, S2. Now you can think of these as ripples in a pond if you throw 2 pebbles down. And then you might want to know if I have an observer here that is receiving these sound waves, and let's say there's a distance 1, d1 from the source number 1. Okay, and then let's say there's a distance d2 from source number 2. Everybody good with that? And let's say the sources are in phase with each other, meaning they go up and down together. They're simultaneous, so they have the same, maybe even the same amplitude, but the same phase, and the same frequency, everything. Okay. Is everybody following that? Okay. Now, clearly, is it obvious to you that if S1 and S2 are in phase with each other, if the observer is halfway between the sources, the signals will just be in sync with each other as well? Does that make sense? They'll add up, right? As long as the distance between the observer and the 2 points is the same, they'll be in phase. Does everybody agree with that? Okay. Because it's the same distance. The waves come with the same number of wiggles. Whatever one does, the other one does. It's the same distance. Now, if the distance d1 and d2 are not the same, but they actually are different by 1 wavelength, do you think they would still be in phase, or they would actually be out of phase? Would they be out of phase? What do you think? In phase or out of phase? In phase, because 1 wavelength doesn't change anything. It comes back and it does the thing again, right? 1 wavelength just repeats. So if d1 is, let's say, 100 meters, and d2 is 100 meters plus 1 wavelength, they're still going to be in phase to the observer. Make sense? Okay, so that's the statement that if the path difference, and let's just put an absolute value so we don't care which one's longer. If the path difference, delta L, which is defined as the absolute value of d1 minus d2. The beauty of this absolute value is you don't have to worry which one is d1 and which one is d2. You put the absolute value, it doesn't matter anymore. If this thing is equal to n times lambda, where lambda is the wavelength, and n is equal to 0, 1, 2. Basically, if it's an integer, then the signals, then we get, we'll just say constructive interference, meaning they add up. They constructively interfere. Any questions about that? So, in particular, if they're exactly the same distance, if d1 and d2 are exactly the same distance, they're maybe in between, exactly in between the 2 sources, then the waves add up together. But as long as the difference in paths are an integer number of wavelengths, they're also in sync with each other. They're in phase. So we also use the term they're in phase. Questions about this? Okay, you can probably guess the next part. If the path difference delta L, which is absolute value d1 minus d2, is equal to not an integer number of wavelengths, but a half integer, or more generally, a half integer plus an integer. So if it's n plus the half times lambda, where again lambda is equal to wavelength, and n is equal to 0, 1, 2, and so on. Okay, this extra half means that now they're out of sync. When one's going up, the other one's going down. Okay, and so they will cancel each other. Make sense? Okay, so in this case, we get destructive interference. Okay, this is what we call out of phase. Exactly out of phase. Questions? Okay, now we get to the very last topic of the course. All right, so in my so there will be, I'm pretty sure there's going to be a demonstration on this, but we're ahead of schedule, so the demo's not here yet. It'll probably come a day or two from now. But it's on beats. What are beats? If you have a sound, like a tuning fork, in fact there's a demo in the demo room, but you'll see it later. Tomorrow or the day after. And you have two tuning forks, and if they're exactly the same frequency, if you bang them together, you just hear that sound. Okay? But if one's just a little bit higher and one's a little bit lower, you actually hear sort of a whoa, 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 whoa sort of effect. That's called beats. And that comes from adding two frequencies that are close to each other, but not exactly the same. Okay, so when frequencies F1 and F2 are close together, the sum of the waves look like this. I'll draw what it looks like. Here's time, t, and here is the displacement for the two waves added together. So I'm adding two waves together. There's going to be this thing which I call the envelope. But the actual signal looks like this. Okay. Here is the envelope. I can prove this to you with math, but it's just one of these sine addition formulas that we did before. If the frequencies F1 and F2 were exactly the same, then the envelope would just be straight. It would just be flat like this. But when they're slightly different, we get a slow oscillation of this envelope. And that sort of wah, wah, wah is coming from the fact that the amplitude seems to be modulating like that. Okay. And there's something called the beat frequency. And the beat frequency is f sub bt. And it's just a very simple formula. It's the difference in the frequencies, and you put the absolute value because you don't care which one's on top of the other. Okay, just f1 minus f2 absolute value. That's the formula. So, very simply, so if you have two tuning forks that you use to tune an instrument, let's say at 440 hertz, that's A, and let's say something that's a little bit flat, so 438 hertz, then you hear beats at frequency of absolute value 440 minus 438 equals to 2 hertz. That's as simple as the beats phenomenon. Okay, this is fine. All right, any questions about that? All right, I've managed to cover everything that you'll learn in this semester, other than the review stuff, which is important. Okay. But we've run out of time for clickers, but if you have your clicker, let's just go ahead and click in for attendance so you get your points, extra points. And as I mentioned, I'm not here tomorrow. We won't do the clickers tomorrow. My student will do the review, and I'll see you guys on Wednesday.
Oh, nice.